Okay, we are back with another video, and the topic of this video is allylic reactions. And the first thing I wanted to do was define what an allylic carbon was. An allylic carbon is a reactive carbon atom that's adjacent to a pi bond. So I'll draw this molecule here, and I'll draw one pi bond in the center. Then I'll start by numbering the carbons. So then we can talk about which one is the allylic carbon. So the allylic carbon is the one adjacent to the pi bond. Well, we see the pi bond here between carbon 2 and 3. So this must mean that carbon 1 and 4 are allylic carbons. And the reason why allylic carbons are so reactive is because they can form stable reaction intermediates. So like carbocations, radicals, or carb anions. And the reason that they can form such stable intermediates is because of resonance. And we know that resonance is kind of just, I have this molecule, but this molecule's electrons in the pi bond could be pushed to here. So perhaps in some time or space, this molecule also exists as these other forms. And let's say I have like a positive charge here. Well, if I move where my pi bond is, then I move where the charge is, right? And in the same idea, this positive charge could be a negative charge. And when I move the pi bond, I've moved where the negative charge is. So by having these resonance structures, we're able to have more stable intermediates because there's more places where our unstable thing, which is like our charge or radical, can exist in time and space. And this lowers the activation energy. You write it down. Activation energy lowered. So it can react more. And another way to illustrate that is, let's say we have our time versus energy graph. This may be a normal reaction, but for allylic carbon, this initial hump is a lot smaller, so then it can react more. So, now knowing that allylic carbons are more reactive than a regular carbon, we can look at our reactions of allylic carbons. The first one I have is, find my time. The first one I have is SN1 sulfurosis reactions, which is just when you have your allylic molecule in an ocean of solvent. And then I've written here that allylic halides react readily. And that's an example of a reaction. The allyl anion stress cation is stabilized by resonance because there's a denuclearized positive charge, which I explained before. So then let's draw what's happening in this reaction. We have our alkyl halide here, and we have our methanol existing here. And methanol looks like this. CH3. So it's on in our SN1 reaction. We know that we can form a carbocation intermediate with this molecule. And this seems kind of weird to us. If we were to perform an SN1 reaction, intermediate forming step here, the electrons from this bond would go to the chloride and would get this molecule, right? But isn't this a primary carbocation? It's not just a primary carbocation, it's a primary allylic carbocation. And as we've discussed before, allylic molecules can form resonance structures. So this molecule actually exists as this as well in time and space. So it's acceptable for us to have an allylic compound. Whereas where we had an alkane, we wouldn't be able to donate electrons to the chloride. This would not happen because there's no stabilization by resonance in a normal alkane. Okay, so we made a little carbocation, but then what happens? So we have our carbocation, and what's going to happen next is that our methanol is going to attack the the allylic. So let's say that in the nuclear that it attacks this molecule. The result of that is this. O CH3 and H. In order to get our product, what happens is our chloride is a strong base. So it's gonna take the hydrogen and deprotonate our oxygen and push electrons back. And I forgot to mention, but 1, 2, 3, 4, 5. The reason this happens is because our oxygen is positively charged here, and molecules like to be neutral. When we do this interaction, we get this and HCl. Both of these molecules are neutral, so they're both happy now. And this is a more stable arrangement than having a negative charge on chloride and a positive charge on our oxygen. So that's what's happening in our Salvalos reactions. Next, we're going to look at SN2 reactions. SN2 reactions we know are going to be backside attack by nucleophile. Okay. So first thing we would do in this instance would be identifying our nucleophile. In this case, it would be our NaOCH3, where the oxygen would be the main nucleophilic atom, and then we look at our allylic carbon molecule, and our allylic carbon would actually be the electrophilic molecule due to the chloride. This chloride is more electronegative than carbon, so then it's going to take the electrons, right? So at the same time, what happens? Cl and A plus OCH3 minus. What NaOCH3 is going to do is that it really wants to bond with the nucleophile. So it's not going to wait for the chloride to just leave. It's going to bond to our allylic carbon and force the bond to break with chloride, leading to this product formation. OCH3 plus NaCl. And something we might be thinking is that, well, in our last reaction, we said that chloride is going to leave. But in the SN2 reaction, this all happens in one step. This is because our nucleophile is a very strong base. It really wants to give away a pair of electrons to another molecule. On the other hand, methanol is not that strong of a base. So it gives time for the chloride to leave on its own. And that's what happens in this SN2 reaction. Next, we have Grignard reaction reagents, and these can deprotonate H2O, DTO, or form carbon-carbon bonds when reacting with a carbonyl compound. So we know how this goes. What we can do is we can take alkyl halide, react it with a acylic molecule, and then we form an alkane and a Grignard here. Alternatively, we can get our allylic halide with Br, introduce magnesium to it, and form our magnesium bromide allylic molecule. Something worthwhile to think of is that what has actually happened here is that Br has a negative charge and this this allylic carbon also has a negative charge, while magnesium has a positive charge. And the same is happening up here with this Grignard. This has a negative charge, while lithium has a positive charge. We draw it as having a bond, but this is what happens in reality. And this helps us understand why we would attack a carbonyl compound. In carbonyl, we have C double bonds to O. And we should know that oxygen is more electronegative than carbon. So we know that the real owner of the electrons in the pi bond is the oxygen. And this makes the carbon have a slight positive charge. And this is what allows our negatively charged Grignard to attack our carbonyl. Hold on. Okay. And the same idea is happening with DO, D2O, and H2O. In this bond, we know that deuterium and hydrogen are less electronegative than the oxygen, so they have a slight positive charge. This allows our Grignard to similarly get a new color, deprotonate the molecule and fully give the electrons to it. And we'll see this happen later on as well. Okay, now we're gonna look at radical allylic halogenation. Here we have an allylic carb molecule, and when it reacts with a di molecule of any halide like bromine or chlorine, we see that the halide substitutes in and then we form an acid. And a real example of this is here. We have this particular allylic molecule. It reacts with NBS and a CCl4 solvent and light. And there are 3 steps we should think about with radical allylic halogenation. That is initiation, propagation, and termination. When we look at this example, we should know that NBS plus HBr creates a steady source of HBr2 via this mechanism. When we have this molecule, NBS has created Br2. What Br2 can do is, due to light will break this bond and give 1 electron to each bromine. This creates bromine radicals in our first step, which is initiation. This bromine radical can then react with our allylic compound here. And we can think allylic compound the molecule is going to react with the allylic carbon, which is not the carbon on the pi bond, but the carbon adjacent to it, which is this one here. This carbon has This carbon is a tertiary carbon, so that means it has three other carbons bonded to it. And the last one is a hydrogen. What's going to happen is this bromine is going, this radical bromine is going to contribute one electron there, and one electron from this hydrogen carbon bond is going to be contributed there. The remaining electron in this bond is going to go back to the carbon. This results in this and all the bromine. Right now, we have let me see, we have a radical on a tertiary carbon. Something that can happen to this allylic molecule is that let me think about how to say this. The pi, the pi bond can be moved to form a different molecule. So while this exists, what can happen is the electron can move here and another electron can move here. And this forms this new radical, which is just a resonance form of this. But then this Br radical can either react with this one or with this one, right? And the question is, how do I know which one it's going to react with? And I have that answer up here. We are either going to make the thermodynamic product or the kinetic product. The thermodynamic product is the most, let me get a new color, is the most stable product. That means it's going to be alkene substitution. The most stable product is going to be the one where the alkene has most substituents. And this is because when our alkene has the most substituents, we're going to have, I believe, let me see, addition to, actually, no, that's all. When alkene has the most substituents, it is the most stable form. So when I say most substituents, I mean this alkene is more stable than this alkene versus this alkene versus this. The kinetic product is then formed by having the most stable intermediate. The most stable intermediate is a tertiary carbocation or a carbanion or a radical. And the reason why it's stable is because of hyperconjugation, which is when we have CH bonds, the electrons in a CH bond can donate into the empty p orbitals of adjacent atoms. And this makes the intermediate stable. And this is the kinetic product because we can think back to our time versus energy graph. Blue, into this in green. Our thermodynamic product may look like this in green, but our kinetic product in pink could look like this. If you have a reaction, right? And okay, rather you have these two reactions going on. The question is, which reaction is gonna happen faster? It's gonna be the pink one, the kinetic product. It's gonna happen faster because it has the most stable intermediate being tertiary over secondary over primary over methyl, right? And it's gonna be favored in kinetic conditions, even though it's a higher energy product than the thermodynamic product. If we have a lot of heat, then the thermodynamic product is going to be favored because we have enough energy to go over this barrier and reach the lower energy product. I hope that makes sense. So then as we think about these, we can look at our allylic molecules below and think, if my bromine forms a bond here, then I'm gonna get this. Off. If my bromine forms a bond here, then I'm gonna get this. Which one is kinetic and which one is, which one is thermodynamic? This one on the right is thermodynamic because we have the most substituted alkene, and that's the lowest energy product. Most stable product alkene, most subs. Next we have the bromine, right? The bromine addition on the left. This one we added to a tertiary radical. Tertiary radical is the most stable intermediate compared to the one on the right, which is a primary radical. So this means this is our kinetic product. Most stable intermediate. Boom. Okay. So our answer for the thermodynamic product will be the one where our pi bond has moved down so that it will be the most substituted alkene. And our kinetic product is the one where we see our bromine added to the tertiary allylic carbon. And that is what we got down here. Let's see. The next thing I wanted to cover was the oxidation of allylic benzoic alcohols with Mn with magnesium oxide. So what will happen is primary alcohols turn into aldehydes and our secondary alcohols turn into ketones. Magnesium oxide only works on allylic or benzoic alcohols. So we should locate all the allylic and benzoic alcohols in our molecule. So down here we have a benzene with 4 alcohols attached to it. So we can look at each one. An allylic carbon is a carbon adjacent to a pi bond. I have 3 pi bonds. Let's look at each one and see if there's an adjacent carbon to my pi bond connecting to my alcohol. For the top left, we can see that there's an allylic carbon here. For the top right, there's an allylic carbon here. Here, there's no allylic carbon on the bottom right, there's no allylic carbon because it's directly substituted. On the bottom left, there's no allylic carbon because the there is an allylic carbon here, but it's not directly bonded to our alcohol. So our magnesium oxide does not work on it. So what happens is we get this molecule where our magnesium oxide only oxidizes the allylic alcohols. This means that the bottom ones stay as alcohols, but our primary alcohol becomes an aldehyde, and our secondary alcohol becomes a ketone. And we should remember this is an aldehyde. Aldehyde has at least 1 hydrogen bond into it, and ketone has 2 alkyl groups bonded to it. And don't forget the pi bonds. Next thing is practice problems. Here we can see above from quiz 1 the concepts that we learned above. This one, I'll go over these quickly. But this one, this is the thermodynamic product because it is the most stable product because there's the most substituted alkene. So this one is the kinetic product because we see a most stable intermediate. We observe addition to tertiary carbocation. And it doesn't always have to be the tertiary carbocation if that doesn't exist. Remember that it follows this order. Tertiary is better than secondary, better than primary, and then better than methyl. Most most stable intermediate. For this one, this follows the same reactions we saw before, where the most stable product is the most substituted alkene. And this one, addition to tertiary radical. So this one would make your thermal product. This one would make the kinetic. And look at that all together here. Next, we can do this one together on the practice stand. For a stepwise reaction for the survivolysis of the compound below. And then we could draw this without thinking of it. We know our thermal product is going to be the one that has the most stable alkene. So all we did here was replace the bromine with our OH and we formed HBr. Oh, we have to draw the mechanism as well here. What happens is bromine leaves. I know bromine leaves first because this is a solvolysis reaction, and that should signal to you that this is an SN1 carbocation reaction. So then I know this is what I have. What happens next is my H2O bonds there. So I get this OH. And this has a 1, 2, 3, 4, 5 positive charge. Next, we still have our Br floating around, right? And this has a negative charge. So it's gonna deprotonate my water, push electrons back to the oxygen, and we're gonna get this. HBr. And we could easily draw our kinetic product as well. It's gonna be this with alcohol adding to addition to tertiary carbocation. Because what can happen here is at our first step, what we can do is push the electrons from the pi bond to the positively charged carbon, and we get this. This is our kinetic product because we've changed from a primary carbocation to a tertiary carbocation, and the same thing happens. Water attacks. This leads to chlorine, H, and then Br attacks, and this leads to H plus HBr. Next is just these two. Oh, wait, isn't this the same as the one before, we know that the thermodynamic product is the product with the most substituted alkene. So all that happens is that our Br changes for an O. A Br changes for alcohol. And we know that magnesium oxide targets allylic, allyl, allylic alcohols, which is this one. It's adjacent to the carbon. It's an alcohol bonded to an allylic carbon, and we know that an allylic carbon is a carbon adjacent to a pi bond. So what we end up forming after we oxidize with magnesium oxide is a C double bonded O and an H. That can be drawn better. And oh, we know this one as well. We want thermodynamic product. So it's just gonna be look at this. Thermodynamic product most substituted alkene. And that gets substituted in plus HBr. That's each other mechanism. You can imagine that there's an H here. We have Br, Br, one Br deprotonates the molecule, and then another Br adds into the molecule. Here, in the second part, we see that we have a magnesium. So then that means that we form a gwynid. If you see magnesium, you should think right away, oh my gosh, I'm with a gwynid. We know that gwynets can deprotonate deuterium deuterium oxide, D2O, whatever, because oxygen is more electronegative than deuterium. So deuterium has a positive charge. And we should remember that in reality, what's happening with the gwynid is that this has a negative charge. Magnesium has a positive 2 charge, and bromide has a negative charge. So the negative charge of the carbon attacks the deuterium and adds it. So what we get is oops, OD negative. Well, I think that's everything about allylics. Hope this was helpful. And let me know any feedback you have. Thank you for watching.